Hello and welcome back to another LeetCode problem. We're going through the advanced graph section in the LeetCode 150 list on leetcode.io. And the next problem we're going to tackle is the LeetCode problem to reconstruct an itinerary. This is a LeetCode hard problem, and we're given a list of airline tickets where each ticket contains a source and a destination representing the departure and arrival airports of one flight. And we should reconstruct the itinerary in order and return it. All of the tickets belong to a man who departs from JFK. Thus, the itinerary must begin with JFK. If there are multiple valid itineraries, you should return the itinerary that has the smallest lexical order when read as a single string. For example, the itinerary JFK LGA has a smaller lexical order than JFK LGB. You may assume all tickets form at least one valid itinerary. You must use all the tickets once and only once. So here we have an example. So we start at JFK, we go to Munich, I don't know which one that is, San Francisco, and not sure what airport that is. But every ticket is essentially an edge in a graph, and that is why we can construct a graph from all of these tickets. And the order here is, because there exists only one itinerary, is exactly the traversal order through these airports. Now, in the second airport, we have actually multiple itineraries, right? So we start off JFK, we could go to Atlanta, could go to San Francisco. Now, we need to pick the itinerary that gives us the smallest lexical order. And the one that gives us a smaller lexical order is when we first go to Atlanta, not to San Francisco. That is why we go from JFK to Atlanta. Then we need to use the ticket from Atlanta to JFK, right? Because we need to use all of the tickets. Then we go to San Francisco. Then we go to Atlanta, and then we go from Atlanta to San Francisco. Right. Another possible reconstruction is exactly what I said. We first go to San Francisco, etc., then to Atlanta, then to JFK, then back to Atlanta, and then to San Francisco. But that's a larger lexical order, since we have JFK SFO, which is larger than JFK ATL. All right, and so this is an interesting graph problem. And it's not as difficult as it might seem. We just really need to be careful with the order of things and how do we achieve the lexical order. And what I would suggest is that we create a graph, but we make sure that the edges that we add to every node are also in lexical order, so that we can be sure that when we iterate through the edges to the neighboring airports, we always pick the smallest lexical order first. And that will ensure that we will automatically find the itinerary that has the smallest lexical order. So, yeah, well, we're going to need to return a result at the very end. Just going to be a list of airports. And what we also need is, well, we need a graph, right? So we could call it flight map. Why not? And it will be a default ticket and a list, and that will contain as a key an airport, and as the values other airports in lexicographical order. All right, so now, well, how do we construct this flight map? Well, we know that we have the origin and the destination in our tickets list, right? So I'm just going to call it source and destination in tickets. Flight map, source, and destination. Now, this is not in lexicographical order, so we have to do this. For source and itinerary, because the itinerary is, the order of in which we were going to visit all the neighboring airports that we have tickets to. from the source airport. Itinerary in flight maps, map items. Well, yes, that's a difficult word for me. And now that we got the itinerary, meaning the list to which we appended the destination airports, well, we just sort it. Now, the next thing is, well, we need to compute what the result is, right? So I suggest that we initiate a little helper method here, def helper. And we're just going to call the helper method from here. And we're going to seed it with the start airport. And we know it's always going to be JFK. And we're going to build up the result. Let's just add the result here as a parameter so that we can easily, extend it when we do recursive calls, etc. And at the end of the helper, we're just going to return the result. So that means we're going to get the result here, and we're going to return the result here as well. So what do we do now in our list? Well, we have to get all of the destination airports, right? So that would be the flight map at source airport. So, well, we can only use every ticket once, right? So how do we ensure that? Well, it doesn't say that we can visit an airport only once. And in the second example, we actually visited the same airport multiple times. Went at least once back between Atlanta and JFK. Same between San Francisco and Atlanta, we visited twice. We can see that because the number of incoming edges to San Francisco is 2, and same for Atlanta. So, and we must use all of the tickets, right? So, well, how do we do that? Well, how about we remove elements from our flight map when we visited them? That's pretty much the only way, but we also want to visit them in a lexicographical order. So if we sort them here in ascending order, if we want to remove an item from the destination list, we have to remove it from the beginning of the destination list, which is an O of n operation. So instead of sorting it in ascending order, we should probably sort it in reverse order. So in reverse order. And now what we can do is we can iterate until we've exhausted all of the different tickets from that airport. So, so the next destination is pop. So we just remove the last element from the list, which we know is the first one in lexicographical order. And then we just call our little helper methods recursively. So we're going to call it here. And since flight map is defined outside, once we've removed a ticket from an airport, we're never going to reuse that ticket again, which is very nice. And so that makes sure that we visit all of the airports. Now, you might wonder why I'm going to do the following: result.append source. Why are we appending the source at the end of the helper and not in the beginning? Well, it has to do with maintaining the lexicographical order. And I would encourage you to take a moment to think why that is really needed. I'm not going to explain it any further. I'm just going to leave that for the viewer. But this means that if we do that, when we get the result back, we also have to reverse the result list, because the JFK, the parameter that we put in first, is the one that we add last. So that means we have to reverse our result list one time before returning it. And that is pretty much everything that is needed. So you can see that it's really simple code. It's not a lot of code for a hard problem. The trick is really with using the list, well, using the edges as a stack from which you can remove elements. You can only, and ensuring the lexicographic order by putting the edges into the stack in lexicographical order, right? And of course reverse, because you can only remove elements from the end of the itinerary array. So let's run this to see if that works. And it does. So you can see it outputs the correct thing. I don't know if we should go through this example to show exactly how this works with the appending the result at the end. Maybe we should do that one time just to make it a little bit clearer. So let's go here. Cool. So we're starting at JFK, right? We're starting at JFK, and but that means we're going to append JFK at the very end. So JFK will be added at the end. JFK. Now the edges from JFK are Atlanta and San Francisco, and remember, in our itinerary list we have them in the reverse lexicographical order. So the first item will be San Francisco, and the second one at the end of the list will be Atlanta. So we're going to pop out that Atlanta node. And we will go into our recursive helper with Atlanta as the next node. But because of that, we already know that Atlanta is going to be the next, or is going to be added just before we add JFK. So we can already put that in. Now we look at what are the edges in the Atlanta node. Well, we have an edge to JFK. So we've used this edge now, right? That's the edge, that's the ticket we've used. So we can't use that anymore. But now we're looking at the edges that go out from Atlanta. One goes to JFK and one goes to San Francisco. Now JFK is lexicographically smaller than San Francisco. That means in our itinerary, we have first San Francisco, then JFK, so we pop that out. And that means we're going to add JFK before we add Atlanta, right? And now again, we're at JFK. Since we've already removed the edge to Atlanta, there's only the San Francisco edge remaining. And we already know that we will add this element as soon as we are done processing the San Francisco airport. Right, so this is in reverse order. Right. This is the insert order into our array. This is inserted last, that before, etc., etc. So now we're at San Francisco. There's only one edge to go from San Francisco, which is to Atlanta. ATL. Now at Atlanta, the only edge left is back to San Francisco. SFO. Yeah, and now this is our result, and obviously it's in reverse order. That's why in the end we had to basically reverse the results one more time, and that explains why we have that in the code. This is why we reverse the result here, and why we append the airport after we've processed flying to all of the destinations from that airport. And because we are removing a ticket every time we visit an airport, eventually we will run out of tickets, and the recursion will end as well. So yeah, that concludes this little problem. And we can check off the next item from our advanced graph list.